All right, let's get right into it. We're looking at something pretty wild today, a new technique that's basically an AI shrink ray. It's all about how to take these absolutely massive AI models and squeeze them down so they can run on everyday devices without losing any of their power. So think about this for a second. How do you take the brain of a giant AI, the kind that runs in a massive data center, and somehow cram it onto a tiny little chip inside your smartphone or your car? That's the huge challenge that this research is tackling head-on. Well, the problem really is that these top-tier AI models, especially the ones doing really complex stuff like object detection, are just enormous. They eat up a ton of memory and processing power, which makes them a total non-starter for the gadgets we actually carry around with us every day. Now, one of the go-to solutions for this is something called quantization. And the best way to think about it is like compressing a huge high-resolution photo into a much smaller JPEG, right? You lose a tiny bit of that perfect, crisp detail. The file size just plummets. Quantization does the exact same thing, but for an AI model's brain. Okay, so that sounds perfect, right? Problem solved. Just squeeze the model down. But, of course, it's never that simple in the world of tech. There's a huge catch, a massive roadblock that makes this whole thing way, way harder than it sounds. And here it is, the big problem. To do this compression, this quantization the right way, you usually need the original data set the AI was trained on. But that data, it's often gigantic, it's proprietary, or it's locked away for serious privacy reasons. So most of the time, you just can't get your hands on it, period. Okay, so if the real data is off limits, what do? You can't just give up. And this is where the researchers got really, really clever. They decided to just go data free. And this leads us to the big idea here. Zero-shot quantization, or ZSQ for short. It's a method where the AI model, get this, generates its own synthetic practice data. It literally dreams up the information it needs to shrink itself down, completely sidestepping the need for any of that private, real-world data. But you knew there was another but, right? This brilliant idea had a flaw of its own. The synthetic data that these ZSQ methods were creating was, well, too generic. It was kind of like a blurry, out-of-focus picture, when what you really needed was a super sharp, detailed blueprint. So for the really tough tasks, this good enough data just wasn't good enough. And here's a perfect example of why that generic data just falls flat. For a simple task, like classification, all the AI needs to do is slap a simple label on something, like person. Easy enough. But for object detection, whoa, that's a whole different ballgame. Now it needs to know the category, and the exact location, and the size of that person. That huge leap in complexity means you need way, way more specific data to learn from. So you see the problem, right? Using that generic, task-agnostic data for something as demanding as object detection, it's like trying to learn brain surgery by looking at a random anatomy textbook instead of watching an actual surgery. It's just missing all the critical details about where things go and how they fit together. And hey, don't just take my word for it. The numbers back this up big time. This chart shows the accuracy, what they call the MAP score, on a standard benchmark. Using that generic task-agnostic data, you get a score of 29.1. Not bad, but with their new task-specific data, it jumps to 30.5. That is crystal clear proof that the kind of synthetic data you use is absolutely crucial. Okay, so this is where we get to the really smart part, the core breakthrough of this research. They came up with this brilliant two-part solution to create the perfect synthetic practice data and solve that blurry vision problem once and for all. And it boils down to this really elegant two-step process. First, they figured out a way to get the model to generate its own perfectly tailored data for the task. And then second, they use a clever training process called distillation to cram all that knowledge into the new, smaller model. So stage one is called adaptive label sampling, and this is where the real magic happens. The AI basically looks inward, using what it already knows to dream up these perfect practice scenarios. It's inventing object locations, sizes, categories, and it refines them over and over again, creating this amazing, high-quality data set from absolutely nothing. It's literally teaching itself from scratch. Then you've got stage two, knowledge distillation. So now you take the original full-sized AI, the teacher, and you have it train the small compressed student network. And what's the textbook? It's that perfect synthetic data they just created. This process makes sure that all the important nuances get passed down, making that tiny student model incredibly smart and efficient. All right, so that's the theory. The big question is, did it actually work? Well, the payoff here is, honestly, it's astonishing. This new method didn't just meet expectations, it completely blew them out of the water, giving much better performance with just a tiny, tiny fraction of the data.
Okay, let's break down the numbers. This table pits their method against the old generic approach on two different AI models. That W6A6 thing, that's just the level of compression. And look at the results. For the YOLO model, the score jumps from 40.7 to 43.0. For the SwinT, it goes from 40.4 to 42.0. In this world, a 2-point jump is a massive win.
But get this is the part that's just insane. They got these incredible results using a synthetic dataset that was just 1/60th the size of the original training data. I mean, the efficiency is just off the charts.
But wait, as amazing as that is, we've saved the most shocking part for last. This isn't just about being more efficient. It turns out, this is about being flat out better. Okay, this is the ultimate showdown. On the left, you've got a model trained the old-fashioned way, with the full, real data set. It gets an accuracy score of 43.4%. Pretty good. But on the right, our method, with zero real data, scores of 45.1%. Let me say that again. With no real data, it didn't just match the performance of a model with all the data, it actually beat it.
You know, it's funny, even the authors of the paper were a little conservative. They wrote that their approach may even achieve comparable results to methods trained with real data. But as we just saw, their own results show they didn't just get comparable results, they surpassed them. That's how groundbreaking this is.
So all of this leaves us with a really profound question to think about. If an AI can create its own perfect learning material, its own perfect teacher, and use it to become even smarter than an AI trained on tons of real-world information, what happens next? I mean, what does that unlock? We might be looking at a whole new chapter in how AI is built, one that's not just faster and more efficient, but also more private than we ever thought possible.